Good morning. So today my seminar topics is these three theorems. So let's see first theorem. First theorem is sequence theorem, which states that suppose that a equal to an, b equal to bn and c equal to cn are sequences of real numbers such that an less than or equal to bn less than or equal to cn for all n belongs to n, and limit of an equal to limit of cn equal to l. Then the sequence bn is convergent and limit of bn would be equal to limit of an equal to limit of cn equal to l. Proof. Choose any epsilon greater than 0 and it is given that an equal to limit of an equal to l and limit of cn equal to l. Corresponding to this epsilon greater than 0, there exist natural numbers k1 and k2. From that we can write these two inequalities, that is modulus of an minus l less than epsilon, that is l minus epsilon less than an less than l plus epsilon for all n greater than or equal to k1, and modulus of cn minus l less than epsilon, that is l minus epsilon less than cn less than l plus epsilon for all n greater than or equal to k2. If k is the maximum of k1 and k2, then since we have choose n greater than k, which implies n greater than k1 and n greater than k2. The above two inequalities hold for every value of n greater than or equal to k. So from these two inequalities we can write that l minus epsilon less than an less than or equal to bn less than or equal to cn less than l plus epsilon for all n greater than or equal to k. So therefore l minus epsilon less than bn less than l plus epsilon, that is mod of bn minus l less than epsilon for all n greater than or equal to k. Hence bn is convergent and limit of bn equal to l, which is equal to limit of an and also limit of cn. The next theorem is, let sequence x is equal to xn converges to x, then the sequence mod xn of absolute values converges to mod x, that is if limit of xn equal to x, then limit of mod xn would be equal to mod x. Proof of this theorem is, let the sequence x is equal to xn converges to x, since limit of xn equal to x corresponding to any epsilon greater than 0, there exists this integer k which is greater than 0, such that we can write mod of xn minus x less than epsilon for all n greater than or equal to k. We already know that modulus of mod xn minus mod x would be less than or equal to mod of xn minus x for all n belongs to natural numbers. So from these two equations we can write mod of mod xn minus mod x would be less than epsilon for all n greater than or equal to k. So therefore limit of mod xn equal to mod x, hence proved. So there is this remark which is, converse of the above theorem need not to be true. So we consider this example. Let xn equal to minus 1 raised to n. Here mod of xn would be equal to 1 for all n belongs to n. Hence limit of mod xn would be equal to 1. But xn would be equal to minus 1 of minus 1 raised to n, which is not convergent. Moving on to next theorem. The theorem states that let x is equal to xn be a sequence of positive real numbers that converges to x, that is limit of xn equal to x, then the sequence root xn of positive square roots converges, and limit of root xn equal to root x. Let's see the proof. Since xn equal to Since x is equal to xn is a sequence of positive real numbers, limit of xn would be equal to x or greater than or equal to 0. We now consider these two cases, that is x is equal to 0 and x greater than 0. First case, let x is equal to 0. Choose any epsilon greater than 0 since limit of xn is equal to x, which is equal to 0. Corresponding to epsilon, there exists a natural number k such that 0 less than or equal to xn, which is equal to xn minus 0, would be less than epsilon square for all n greater than or equal to k. 0 less than or equal to xn be less than epsilon square for all n greater than or equal to k, which implies 0 less than or equal to root of xn less than epsilon for all n greater than or equal to k. Since epsilon is an arbitrary, this implies that limit of root xn equal to 0, which is equal to root x. And now the second case, let x would be greater than 0. So modulus of root xn minus root x would be equal to mod of root of xn minus root x into root of xn plus root x divided by root of xn plus root x. That is, we take the conjugate of modulus of root xn minus root x, which would be equal to mod of xn minus x divided by root of xn plus root of x. Since root of xn plus root x would be greater than or equal to root x, which is greater than 0, from the above inequality, it follows that modulus of root xn minus root x would be less than or equal to 1 by root x of mod xn minus x. Since limit xn is equal to x corresponding to any epsilon which is greater than 0, there exists a natural number k such that modulus of xn minus x less than epsilon of root x for all n greater than or equal to k. From the first equation and second equations, we can write that mod of root xn minus root x would be less than 1 by root x epsilon root x, which would be equal to epsilon for all n greater than or equal to k. Since epsilon is arbitrary, this implies that limit of root xn would be equal to root x. So that's all. Thank you.